We want to test the series for conversion or diversion. When you look at this series, hopefully you can recognize that is of the form of a p-series. Therefore, I'm going to use the comparison test, the limit comparison test. So for the limit comparison test, we need a sub n, and b sub n. So a sub n, in this case, is going to be n squared minus 1 over n cubed plus 1. And b sub n is going to be 1 over n. Taking the limit, as n approaches infinity, a sub n over b sub n. We'll see that we ended up with n squared minus 1 over n cubed plus 1. And then I'm going to multiply by the reciprocal. So I'm going to multiply n here. So we can simplify it. So this is n cubed minus n over n cubed plus n. Now, since we want to take the limit, I'm going to divide everything by n cubed. So we ended up with the limit as n approaches infinity, 1 minus 1 over n squared over 1 plus 1 over n cubed. And this one is going to go to 0. This one's going to go to 0. Therefore, the limit is 1, which is greater than 0. Since 1 over n is divergent because it's a harmonic series, our current series is divergent as well. For this series, you can see that we have a constant raised to the power. Therefore, we should use the ratio test. So I'm going to take the limit as n goes to infinity, a sub n plus 1 over a sub n. So we're going to have our series, taking the limit of our series, so we have n plus 1 to the 4th power over 9 n plus 1. And since I divide, I'm going to multiply by the reciprocal. 9 to the n power over n to the 4th power. So now we need to simplify it. So what I have is n plus 1 to the 4th power over 9 n to the 4th power. I'm going to take out 1 over n. I'm sorry, I'm going to take out 1 over 9 and taking the limit of 1 plus 1 over n to the 4th power. So you can see that that one's going to give you 1. So this one right here is going to give you 0, so we're left with 1. So it's going to be 1 over 9 times 1, which is 1/9, which is less than 1. So the series is absolutely convergent by the ratio test. For this example, when I take a look at a sub n equals to f of n, the function right here, and it's easy to evaluate, I'm going to use the integral test. So when we use the integral test, you need to check for the hypotheses, and there are 3 of them. So first, we let f of x equals to x to the 8th power, e to the negative x to the 9th power. So f is continuous. That's the first hypothesis. It's positive on 1 to infinity, And we have to check whether the function is decreasing or not. So in order for us to check for decreasing functions, we're going to take the derivative. And the derivative, I'm using, you can use a product rule for this one. And after you take the derivative, this is the function. E to the x to the ninth power. This one right here is gonna be negative. So for x greater or equal to 1, f is decreasing. So we're gonna have to take the integral. So I'm gonna take the integral from 1 to infinity x to the 8th power e to the negative x to the 9th power d of x. So taking the limit, I get t goes to infinity. And then I have negative 1/9 using the u substitution. I came to that function, and then we want to evaluate from 1 to t. So it's going to give us 1 over 9e. Therefore, this series converges. For this series, since we have the negative 1 to the n minus 1, I'm going to use the alternating series test. So first of all, we have to identify b sub n. So b sub n in this case is going to be 1 over square root of n minus 5 for n greater or equal to 26. Notice that we start with n equal to 26. So you can see that b sub n is decreasing. A sequence of positive numbers, and then we take in the limit of p sub n, which is a limit n goes to infinity of 1 over square root of n minus 5. You see it's gonna yield to 0. So our original series converges.